asymptotic symmetries from the string worldsheet. Let's welcome Wei.
Thanks, Janet, for the kind introduction. It's a great pleasure to give a talk in this wonderful conference. The talk is based on two papers in collaboration with my students. Here is Zheng Yuandu and Wenxin Lai and Kangming Liu. Lai Wenxin has already graduated and he is going to ICTS. So as you can see from the title, my talk contains two main ingredients. One is asymptotic symmetry. The other is the string worldsheet, string symmetry. So as we know, symmetry has played a crucial role in the development of modern theoretical physics. Even in this conference in ICTS, we already heard a lot of talks related to symmetry. We heard about Xiao Guri talking about global symmetry, and Maria Svetic and Jonathan Hetman and Kupastan, and talking about hair symmetries and generalized symmetries. And asymptotic symmetry is yet another type of symmetry that is not directly related to what the other speakers have talked about. So what are asymptotic symmetries? As we know from kindergarten, we know that Noether told us in a theory of quantum field theory without gravity, we all know how to deal with symmetries, more precisely continuous global symmetries, right? Whenever there is a global continuous symmetry, then Noether already told us how to write down or conserve the current and furthermore, this conserve the charges. And another charge will generate this symmetry transformation and map physical states to physical states. That's one of the most important symmetry is the time translation symmetry, and it gives us energy conservation. And the charge that generates time translation is, of course, the Hamiltonian, right? This is the story, the familiar story without gravity. But once gravity is introduced, things become trickier. Because as we all know from the general framework of general relativity, time translation is nothing special. It is just a part of diffeomorphism, and general relativity is a theory with covariance, and coordinate transformation just look like a gauge redundancy. And for gauge redundancy, how can it generate a time evolution? How do you write down a Hamiltonian? And how do you define energy in a theory that contains gravity? And that leads to the notion of asymptotic symmetry. Time translation is, you should really think it as a part of asymptotic symmetry instead of the Euro notion of exact symmetry that we were all familiar with. How do we deal with asymptotic symmetry in a gravitational theory? Well, then let's go back to the theory itself. A theory is always defined by the action. Well, that's not enough. Action itself doesn't define the action, the theory. You also need to impose certain boundary conditions. The action and the boundary conditions altogether will give you a definition of the theory. So once you made a choice of your boundary conditions of your theory of gravity, then all the diffeomorphisms, all the coordinate transformations that you thought would be redundancy will be classified into different classes. Some of these diffeomorphisms will violate the chosen boundary condition, and then these these are not allowed. You're not allowed to do this diffeomorphism. Some of them are just too small. They just do something in the middle of the space-time and does not affect data in the asymptotic boundary. Then these are the gate redundancies, and they just the theory, the hierarchical space has to be modeled by these trivial transformations. The most non-trivial thing is, roughly speaking, the symmetry transformations. That's something at the boundary, but lead to but still obey your chosen boundary conditions. And these allowed symmetry transformation and mod the trivial symmetry transformation will form this asymptotic symmetry pool. And to consider symmetries, to consider energies in a theory of gravity, what you have to do is to talk about it in the context of asymptotic symmetry. And so this actually, this discussion have been initiated in the early 60s by this famous BMS group, and also in this in the 80s, Brown and Hanot used this logic to discuss the asymptotic symmetry of three-dimensional gravity asymptotically anti-zeta space-time, and what they found was, well, two sets of Wei-Song generators. And that was way before the first example of ADS-FT realized by Manasena in string theory, right? So back then, we would have seen that the phase space of Einstein gravity in 3D with Brown-Hanot boundary conditions has the same phase space as that of two-dimensional transformer field theory. That's actually a prelude of ATS-3 correspondence. And it turns out this idea of using asymptotic symmetry analysis to try to find some clue of holography can be generalized to more general space-time background. So we know ADS-CFT is the correspondence between gravity asymptotically anti-zeta space-time and conformal field theory in lower dimensions. But there are more interesting space-times which does not fall into this class. They are not asymptotic ADS. For example, flat space and also this the zeta space, which is relevant in early universe, and there are lots of other interesting space-times. And if we want to use holography to enter quantum gravity in static space-time, we really need to push the idea of holography beyond the known framework of ADS-CFT. And the idea of using asymptotic symmetry analysis has been very fruitful, as Professor Bin Chen mentioned earlier today. We can use asymptotic symmetry analysis to find some clue to the holographic field for extreme occur space-time and also the zeta space with certain modified boundary conditions. And that's the power of using asymptotic symmetry analysis. On the other hand, speaking of holography, there are in general two approaches of doing holography. So what I have just mentioned using using asymptotic symmetry analysis to find this, the simple structure is one method in the so-called bottom-up approach. The idea of bottom-up approach of doing holography is we just start from effective field theory. We know no matter the full quantum version of gravity is, we know the low energy effective theory is this instant gravity capitalism matter, and just starting from that, and we can use some tools to study some very universal properties, and that include knowledge of black hole physics, and we learned a lot using this bottom-up approach. Then there is also the other approach. This is the top-down approach, where you start from known UV completion of quantum gravity, for example, string theory. You start from there and really build your theory of holography seriously, and you just point out which theory of gravity is equivalent to which step key. And there are a bunch of very explicit examples. For example, the most famous one is what Manasina told us in the 90s, this type 2B string theory on ADS5 cross F5, and it is equivalent to for superunit theory. And there is another one which is more related to the talk today, that is type 2B string theory on ADS3 times CS3 times E4, supported by NS3 form flux. And this is a realization of ADS3 CFT2 in string theory. So I already mentioned that in this bottom-up approach of ADS-CFT, asymptotic symmetry has played a very important role. Now I want to ask the following question. How can we see asymptotic symmetry in the top-down approach? How do I see it in string theory? And more explicitly, how do you see it on the string worldsheet? And that is the title today. So first, before going to the worldsheet, let's review how these symmetries, asymptotic symmetries, can be found in gravity, in supergravity. So let's say let's be more explicit. This is a 3D gravity, and then we know ADS3 in Hungarian coordinate can be written in such a way where phi is a radial coordinate and UV are two latitude coordinates. They will parameterize the two-dimensional boundary where the CFT lives. So the asymptotic boundary is taken as this phi parameter goes to infinity, and we know it this ADS has this local asymmetry SL2 plus SL2. So let's do the procedure in a very explicit way. We can impose a boundary condition to a class of solutions, to the class of the solutions of this theory. Usually we can do it in the so-called Fermat-Graham gate, where everything, we just expand the 2D metric GIG in terms of in order by order in last 5. And the Brown-Hanot boundary condition is to say that the change of the of this 2D metric Gij can only be of order 1, but it cannot change the leading order growth of this matrix. So once this boundary condition is chosen, then you can ask what kind of vectors. If I suppose I have a vector C, if I act this matrix by the vector, and this is the Lie derivative. Seeing a vector is an asymptotic scaling vector is to see that this Lie derivative is of the same order as our boundary condition. So this will allow us to solve all the possible form of this vector, and that's for Brown-Hanel boundary condition. We get like 2 families of solutions, parameterized by the left moving coordinate and right moving coordinate respectively. And of course, we all know that they form this weight algebra under the Lie bracket. And then for these asymptotic scaling vectors, we use Noether's procedure to derive the kinds of the charges associated to these vectors. And these Q's are this Fourier mode of the charge of this one of the Fourier mode of this asymptotic scaling vector. And these the charges will form an algebra where the direct bracket, and the result is that we get a very thorough algebra, and the central charge is determined by the ratio between the ADS length L and the 3-dimensional Newton's constant G, the 3L over 2G. And for pure Einstein gravity, we can further write down all the allowed solutions of this under this Brown-Hanel boundary condition. So to summarize, what we need to do to find asymptotic symmetries in supergravity is the following. The first step is to give a consistent boundary condition, and then find asymptotic scaling vector, and then find another charges, and then calculate algebra. That's the steps we need to follow in a series of gravity. So now we're ready. We can try to understand how do we do something very similar but on the string worksheet. So again, before going to asymptotic symmetry, let's first talk about the exact symmetry on the string worksheet. Let's just review what Korchinski chapter 1 told us. So we have, suppose we have a background with metric G and B field B, and then that's the worksheet action in the conformal gauge, where X are the target space ordinates. So we know in flat space, we know that the space-time has asymmetric group, the Poincare group, right? How do we see Poincare group on string worksheet? They are global symmetries on the string worksheet, right? And so basically, we just for each of these Poincare generators, we can just follow the standard way of another procedure and find another targets, and they just we can find them. We know how to express them on the worksheet. And what's more is that this Lorentz group and Poincare group, they help us organize the states. The string worksheet differential motion and the very thorough constraints, they have to be invariant under this asymmetry transformation, space-time asymmetry transformation, and in the end of the day, the physical space are also organized by these symmetries. So these are exact symmetries, right? And now we will go from exact to asymptotic. Then we have to see what do we mean by asymptotic on the string worldsheet. So then as we have shown in the example of ADS spacetime, so in ADS spacetime, there is a radial coordinate, right, which we call, we parameterize as the phi. So suppose we have a target spacetime where there is some radial coordinate. That's also call it phi. And suppose the boundary, the target spacetime boundary, is also taken as phi goes to infinity. And then what we want to impose as the condition of an asymptotic symmetry on the string worldsheet on such a class of spacetime is the following. We want our worldsheet equation motion is preserved asymptotically, and also the versor constraint is satisfied asymptotically. So here asymptotic means all these equations are satisfied up to certain orders in this large phi expansion. And in explicit models, we'll further specify how each equation falls off. That's we'll see later. So, yeah. Yeah. The chart have to commute with the statistics. Okay, so once we have specified what we mean by asymptotic symmetries on the string worldsheet, then we again another also told us how to write down the corresponding charges. So these asymptotic symmetries in the target spacetime is now realized as the asymptotic global symmetry on the string worldsheet in the sense that specified here. And then by solving these conditions 1 and 2, and we will find the asymptotic Taylor vectors, just like the cases that we found in the case of gravity. And then once we have this asymptotic Taylor vector, then we can just write down the asymptotic another charges on the string worldsheet, and these charges will just generate this transformation. And finally, the physical states of string theory on this class of spacetime will form representations of this asymptotic symmetry.
Asymptotical things, actually, because the phi is a coordinate in target space, right?
It is a coordinate in target spacetime, and it's a field.
Field in the worldsheet.
On the worldsheet.
On the worldsheet. So when you talk about the asymptotical properties of the worldsheet theory, you are talking about some property when this field is take very large value.
Yes.
Okay.
Yes. You can say at the classical level, we are looking at a particular corner of the space. Okay, so any more questions? Okay, then let's let's proceed. So now, let's see suppose we have solved this condition 1 and 2, the asymptotic equation motion and reversal constraint. Then how do we write down another charges? We can do it in either the Lagrangian way or the Hamiltonian way. There are some subtleties, but the main idea is as follows. In the Lagrangian formalism, suppose we have this asymptotic Killing vector parameterized by this cosine. These are again spacetime vectors, but they are fields on the string worldsheet. And sometimes it is this vector is also has to be compensated by a gate transformation to the B field. So let's say asymptotic Killing vector contains this C and this lambda. Then we can, if that's the standard another way, we work out to the variation of the action and then just write down another current. And most generally, for arbitrary C and lambda, the variation also contains this vortex term. So for exact symmetry, the vortex is exactly 0 because if it's if it's asymmetry, this is just 0. But for asymptotic symmetry, we can require that this when we go to the asymptotic region, but it's to infinity, and this vortex is also 0. If this is true, then we have this conservation law, and we can just define the Euro another charge, conserve another charge from this current. And then if we can do so, then the algebra we can just calculate using the standard technique, using this OPEs on the string worldsheet. Now, we can also consider do it in the Hamiltonian formalism. So how do we discuss more general or general symmetry in the Hamiltonian formalism? Well, let's first consider the free space parameterized by coordinates x and their conjugated momentum. And then we can, on the free space, we can define, there is always a symplectic structure, there's omega. And then if we consider a diffeomorphism in the free space, then it is generated by a variation of the free space coordinate Q. And then suppose it is a symmetry is generated by a certain Hamiltonian, let's call it HC. Then by definition, the variation of the flow in the free space is generated by boson bracket, where boson bracket is determined by the symplectic form. So for arbitrary functional T, the flow of it, or the variation of this P under this symmetry is also given by this Hamiltonian, by the boson bracket with the Hamiltonian. Now, because this P is functional in the free space, we can also say it is. We can use the chain rule to work out the variation. It's derivative with respect to the coordinate and times the variation of the coordinate. And using these two definitions, we can just read off this variation in the free space and this this phase space vector C, and it is related by the Hamiltonian that generated in such a way where there is symplectic form. So this way, it allows us to basically solve this this generator by integrating this formula. So we get this infinitesimal Hamiltonian that generates this transformation C by this formula. So we see this is infinitesimal Hamiltonian in the phase space. That means that if we it is defined only at it is defined at a point in the phase space, and it is if we want to go finite distance away from this chosen point, we have to try to integrate this infinitesimal relation. And it is there is some subtlety. Sometimes this chart is not integrable, but in the case this is integrable, we can get a finite chart, and formula can be written as this integral. Okay. So there is a further subtlety. So we are more familiar with diffeomorphisms on the that act on the coordinate. And once we know a diffeomorphism that acts on the coordinate, how do we know how it acts on its conjugated moment? There's some conditions that we can use to determine it. First of all, we notice that the chart, in order for this chart to really be a symmetry, it has to be conserved. That which means that it commutes with the Hamiltonian. And furthermore, this evolution, the symmetry evolution, it has also to be compatible with the equation of motion. So combining these two actually will help us to determine this vector in the momentum directions. This is some subtlety, and it's not. It's helpful with the calculation, but conceptually, it's not maybe not that important. In the end of the day, this what I want to say is that in the Hamiltonian formalism, there is also a way to write down the chart that generate this certain symmetry. Suppose you are given an asymptotic Killing vector that acts on the coordinate. There's a procedure to do so. Okay, so that's for formalism.
Is the ambiguity related to the charges, a kind of diffeomorphism that dies off at infinity?
Yes, because so for exact symmetry, it's okay. The main thing is that for asymptotic symmetry, you are really considering a class of spacetimes where this basically the direct variation, you are already using a particular relation between coordinate and the momentum. That's essentially some exact equation of motion, right? So you have to give that out. Yeah. Okay. Okay. So there is on the worksheet. What I want to point out is that we can find, we can impose some boundary conditions. That is to say that the equation motion is and the Versor constraints are both satisfied in the sense of asymptotically satisfied. And then once you have this, and you just solve it, you find the asymptotic Cannon vectors, and then you just either follow the Lagrangian formalism way or the Hamiltonian way to write down the number of charges. And then once you have that, you can find the symmetry algebra. That's the main procedure to find it. Find the symmetry and the algebra on the string worldsheet. Of course, in the Lagrangian formalism, you can use OPE to calculate the algebra. And in the Hamiltonian formalism, it is more natural to do it step by step. If you have difficulties in the Lagrangian formalism, you need to go back to the classical version, and you have this Hamiltonian way, you have the boson bracket, and then you go ahead with this canonical compensation. In principle, you can go all the way to the quantum theory. So that's the formalism. Then let's look at some examples. First example is let's say consider string theory in flat space. And suppose, of course, superstrings has to be told in 10 dimensions, but now let's just look at the 3-dimensional part. And suppose the other 7 dimensions are just some small compact manifold. So why is this interesting? Because in the gravity analysis, people have already found that this 3D flat space, you can go to the boundary gauge and found this so-called BMS algebra at now infinity. So here is the BMS algebra. It's generated by these L's and M's. L's are the super rotations, and M's are the super translations. So basically, if we use the boundary gauge, the super rotation is basically a reparametrization of the theta. And super translation is to shift this retarded time u by arbitrary function of theta, arbitrary periodic function of theta. Okay, so if we consider pure Einstein gravity, this BMS algebra has this central charge CL equal to 0. And Cm equals to 3 over G, where Cm is the simple term between the super translation and the super rotation. So that's the gravity, gravity result. Now, let's look at the string worldsheet. We put flat space Minkowski in boundary gauge to on the string worldsheet. So this is just the bosonic part, and there's no other background field, just the metric. And
You're taking the 3 coordinates as fields on the 2-dimensional worldsheet, right?
Yeah.
In a quite similar way as the target space, right?
Yeah, the
Okay.
3D Minkowski is the target space.
I see. Okay, thanks.
Okay, so this is the equation motion. Now, as I mentioned in the general framework, our next step is to try to find the asymptotic vector and there are two rules, right? One is that the equation of motion, worldsheet equation of motion, is satisfied asymptotically. What do I mean? So consider I do a space-time diffeomorphism generated back C. Then I would like to require my equation of motion. My equation of motion is satisfied up to certain order in large R expansion. In flat space, in bounded gauge, R plays the same role of phi. It's a radial coordinate. When R goes to infinity, you reach square plus, which is now infinity. So, for example, this variation of U is the U component of C, and plus CR, and this is not necessarily zero, but it is zero up to order 1 over R. And similarly to other components of the equation. So this gives some constraints to this vector. And for example, you take this answers and you plug in, you will find the solution. And this solution, you see, it is parameterized two arbitrary functions, f theta and y theta. And actually, they just correspond to super translation and super rotation. They are just the same BMS generators. And of course, here we also found something interesting, something extra by just solving this asymptotic equation of motion. Also found that there is a dilatation operator which rescales R and U in the same time, also preserves the worldsheet stress tensor, and this actually this is also discovered in some other discussions. This is one of these so-called it is actually a conformity vector, and people call this conformity BMS. But however, we want to we also want this is just the equation of motion. We also need to check that the Virasoro constraint is also satisfied, because that's imposed the physical condition, right? So this dilatation operator is actually not part of the asymptotic symmetry rules in our sense, because we want to preserve the stress tensor. But maybe it is interesting for other purposes. Okay, now we can try to write down the symmetry generators, and here's the formulas. And then we find that then these generators, as we can see, they are all functionals of our target space coordinate.
In the previous slide, where you said this dilation generator, you don't consider it because it's not a part of the asymptotic symmetries under the boundary conditions. But where? Oh, that's what you mean by. Oh, I see. Okay. I mean, one could change the boundary conditions so that at the level of diffeomorphism, you still preserve those boundary conditions. Like you could have the equations of motion and the boundary conditions of the metric, I mean. Like the boundary conditions satisfied by the metric. Maybe my question is, can you change the boundary conditions on the metric, like the fall-off conditions, so that this is still a part of the symmetry generator?
Yeah, that's this people.
That's what they did.
From worldsheet by boundary conditions, I only and this equation motion and the stress tensor preserved. That's what I can say from the worksheet.
Oh, I see.
Yeah.
So to get the result, you would need to, what would you need to do? Would you need to add something?
Well, it's actually it's not super clear because here I want to preserve asymptotic physical data. The physical here the space is preserved, but there there's okay. The standard BMS doesn't contain this thing, right? It's when you are actually enlarging the theory, right? By allowing this more general like BMS conformance.
Just because if alpha prime appears in the denominator, and if that goes to 0 in the string sigma modulus like a tensionless theory,
It's not clear. Maybe it's
when and then also because it would be very natural to have a dilatation symmetry in the massless limit of the theory. So maybe if there's a way to interpret this limit or take a related limit where it's where we think of the string tension as going to 0.
maybe there's.
Right. So very quickly, what did they need to do? These references?
Well, maybe we can discuss.
Okay.
So the worldsheet asymptotically close to this asymptotic space, then this equation of motion satisfied. What happens if this you have the internal space? I mean, this is like a large non-packed ones. You have an internal space.
Yeah. Nothing changes in the just focusing on the three-dimensional non-compact part. So how many minutes do I have? I have 30 minutes. Oh, 1-3. Oh, 1-3. Okay. Okay. So yeah. So then we can calculate the BMS charges from the string boson bracket calculation. Here we still we can't find the simple term. Well, there's as I mentioned in gravity calculation, there is a central term with Cm non-zero, but here it's still centralized. As we'll see in the next example, usually this simple term is related to non-trivial topology. And here, maybe one of the reasons is that here I'm just considering just a flat space. There's only metric. There's no B field. Maybe there is a way to restore this simple charge term later. Okay, that's the story of this first example.
Sorry, when you say topology, you meant topology of the worldsheet?
Yeah. So let me quickly go through this type 2, the second example, type 2B string theory on ADS3 with certain internal manifold. So there we have some very explicit, in some special cases, there is a very explicit proposal for the CFT. And also we know when this type 2B string theory is supported by this NX flux, there is weakly coupled string worldsheet description. And the ADS3 part is this SL2 WCW model. And so let me just mention some notations where K is the level of this SL2 WCW model, and it is also related to the length of ADS3. It's K equal to L squared over R of N. And we'll probably not need P, but the P is this, as I mentioned, there's NS flux, and K is the magnetic charge, and P is the electric charge. It's the number of the fundamental strings. So what's happening with this model? There's the background. We have the ADS3 matrix as we wrote before. In addition, we also have an anterior B field. We say that it also grows. It goes e to the 2 pi at the boundary. It's growing up. And it has two legs in U and V in two boundary directions. And there's also some deleter. So this is this phi. This phi is not that phi. The phi is a metric, is the radial direction, and in addition, there is also a deleter. And here's the worldsheet action and equation of motion, space tensor. Now we can just proceed with the in our way of finding the asymptotic K-link vectors, and no surprise, we will find the two the left moving and right moving source generators on the worldsheet. And then we can also follow the procedure and find the charges that generate this transformation. And these charges they will form an algebra, and we can either use the OPE or the Poisson bracket. And see here, there is a simple term, right? So this simple term is actually is something. It is not a constant. It is something like C equals to 6A times C P sigma du, something like that. So where U is it is a coordinate. We are by doing this asymptotic analysis, we usually compactify the boundary of ADS. We put it on. We consider it is a cylinder where there is a circle U V U pi with U pi. So we see then this U can have a natural winding when sigma, the worldsheet sigma, when we consider closed string, go from 0 to 2 pi. So this is actually a winding. So this the algebra, Versor algebra on the worldsheet actually it's the simple charge is it's an operator instead of just a pure number, but it is sort of it is topological. Okay, so this is the story of ADS.
Oh, so you mean that the central charge of the asymptotic algebra depends on the shape of the worldsheet, the topology of the worldsheet?
Yeah,
Then how do we understand it from in usual ADS CFT? We would think that the central charge is fixed of the dual theory of the bulk. Then does that mean that this is not correct? It's some average of different.
Well, there's indeed some recent discussion for thinking of this string theory as some sort of like example of symmetric product CFTs. There is indeed some discussion like that.
And this kind of strings are very large.
Yeah, it wraps the boundary circle.
Maybe it's exponentially suppressed because it's so big.
No, they are not suppressed.
Oh.
The long strings, because it's essential because to have this D field. So because it's sort of it's part like gravity is attraction, and then this B field will push it away so that it can still stay balanced. There can be lots of long strings lingering at the boundary of ABS.
Very intriguing.
So these operators have previously discussed in the papers in the 90s, but we just reproduce it in our own way, and there's also some subtleties, technical subtleties. Anyway, so this is the story of ABS3, and so then let's go to the third example where the symmetry is not quite clear before, at least not discussed in the string worldsheet. So this is the example of the so-called TTbar correspondence, and where we already mentioned this inner triangle. So the TTbar correspondence is to do deformation to all these three columns. So in the WCW and the supergravity on ABS3, they are all regarded as the buffer theory. So here we perform the so-called TST transformation, where T is a T duality, in our case, a T duality along U direction, and then S is a shift, like V goes to V plus lambda U, and then T duality along U again. So this is the TST transformation, and this transformation will lead us to new background where strings can propagate. And I will see how it looks like, but the most important feature of the new spacetime is it is no longer asymptotic ABS. So by a TST transformation performed to this ABS background, we will obtain some new asymptotic ABS3 background where string can still propagate. This is the bulk story. TST is the deformation in the bulk, and then TTbar refers to the corresponding deformation in the field set. So there might be a more general deformation of what the field theory is, but for in the special case where there is a symmetric product structure, the boundary deformation is to perform the Euro TTbar deformation to the seed theory of the symmetric product, and then you do p copies of that, and then mod the theory by this permutation group SP. And by this way, you will construct the so-called single phase TTbar deformation. And so on the worksheet, TST transformation, there is some very explicit formula that relate the deformed data of G and D. So M is G plus D, which is M here, and the undeformed data, M tilde. And this mu hat is the deformation parameter. So there is a well-established relation between the the background before and after the transformation. And if you take the derivative of the deformed TST transformed string worldsheet action with respect to mu, you'll find that it has the same structure as this TTbar deformed theory. Namely, the right-hand side is just this only depend on the stress, the not occurred corresponding to the two Latin coordinates. So that's a very quick review of this TST TTbar correspondence. What we have known is that for a TTbar deformation, we can write down the spectrum, and for some region of the parameters, we can read the entropy and then matches to the black hole entropy. And there are certain there's a list of things that has been verified so far. But I want to point that recently there is also some progress in the calculation of correlation functions. Correlation function, calculating correlation function in TTbar deformed theory is very difficult because the deformation is irrelevant, and you quickly lose control if you do it perturbatively. By using this TST TTbar correspondence, we can just quickly read it from the string worldsheet, and this is work with Wei Song and Wang here. So we have something very neat. Suppose we have a two-point function and of operator with conformal weight h and h bar before the deformation, and then you can take the two-point function and do Fourier transform and go to the momentum space, and then just to replace the momentum space two-point function by just replace the original h by the shifted conformal weight, and then you get this very neat formula. It has it's very structural, right? So and it also it is consistent with some independent calculation by the group by Aharoni et al. So it suggests that the simple form of this two-point function suggests that maybe there is some there governing this the theory, organize the states. So then we look at asymptotic symmetry in this model in the string worldsheet theory. How many? Randomly, okay. So the upshot is we find non-local coordinate transformation. So you see this U is the coordinate, U is the coordinate after the TST transformation on the worldsheet, and U phi is after TST, and this capital uppercase phi and uppercase U are are related to this that such a non-local or coordinate transformation, and this capital uppercase hat fields they have the following property. They satisfy the same equation motion of this WCW model, same stress tensor, and same boundary conditions under this circle on the worldsheet, and also that some choice of some zero mode parameter, we can also match this symplectic form. Why do I stress the symplectic form? Because suppose we start from a field redefinition, only map is sort of classical, right? Map the solution to solution. But this is not enough to say the two theories are related at the quantum level. But if, in addition to that, it also has an identification of the symplectic form, then we can proceed with canonical compensation. And in principle, at the quantum level, it is possible to establish equivalence between the two theories. So now, this means that we can use the data or the results of the string theory on ADS3 or second example to study the theory after the TST transformation. So what we have is that, of course, in this head coordinate, we've already shown that there is the star, we have the generators, and then by following this map, we'll be able to basically rewrite all these generators in our physical coordinates, with liquid view with that coordinates, and get the transformation there. And also there is a set of unrevealed generators that is related to the other one. That this vector, this rescaling is to make sure that the zero mode here are the energies that translate that correspond to mu and wave translations. So that's the story here. You can see that in this basis, the algebra is highly nonlinear and non-local. It's very complicated. But nevertheless, there's something we can write down, and it is consistent with known results so far. Hope there's something more to be explored. Thank you.
Questions?
So if we consider worldsheet with boundaries, so this boundary will have some, in space-time, will have some boundary condition of this difference. So see, that kind of both will be asymptotic, some sense.
You different?
Yeah, I mean, you have worldsheet, you have some boundaries, and this boundary will be, on the difference. Yes.
Yeah, we haven't thought of the difference. So here we are just considering closed space.
Yeah, your IDS is kind of set of difference.
Yeah,
And
we
you can also have,
that.
a worldsheet with boundaries.
Other questions? Outside. So if there are not other questions, let's thank Song Wei again.